Now.
Yes.
Okay. So, good day, everyone. I will be discussing the homework 5, question 1, and question 2. So, for the first question, we have the ethanol is produced commercially by dehydration of ethylene with chemical balance equation C2H4 plus H2O is equals to uh, C2H5OH. And some of the product is converted to diethyl ether in the side reaction of 2 moles of C2H5OH is will be the product will be C2H52O plus H2O. So the feed to the reactor contains ethylene, stream, and an inert gas. A sample of the reactor effluent gas is analyzed and found to contain 43.3 mole percent ethylene, 2.5% ethanol, 0.14% ether, 9.3% inerts, and the balanced water. Okay, so there are two chemical balance equation that are mentioned. So we must first identify the main equation, which is the hydration of ethylene to produce ethanol, and the side reaction, which is uh, 2C2H5OH will be its product will be C2H52O2 plus H2O. So to answer we're going to discuss the first question now. Take as a basis 100 moles of effluent gas. Draw draw and label a flowchart to a degree of freedom analysis based on atomic species to prove that the system has 0 degrees of freedom. So the unknown here is the input reactants. It it's it said that there are the moles of input has ethylene, uh, water, and then the moles of inert gas. And so it is said that we should assign the total moles of output to be 100 moles, and then the given percentage of I mean the given molar fractions of um, ethylene, uh, ethanol, ether, inert gas, and then the balanced water are given. We're going to integrate those given informations in the output. So next that we're going to do is after we do the flow chart, we must do the degree of freedom analysis. Okay. So since it is a single unit, we will be doing a degree of freedom in this whole unit with analysis based on atomic species balance. So from this system, we have three unknowns, which is N1, N2, and N3. And then we have two atomic balance species, which is carbon and oxygen. Um, as you can see here, there are three uh, chemical elements that are involved, carbon, hydrogen, and oxygen. But the only independent chemicals are carbon and oxygen, because if we're going to look back on our main equation, carbon and oxygen are independent, while the hydrogen can is yielded on is yielded on two compounds, which is C2H4 and water. So therefore, the only two independent atomic balances are carbon and oxygen. And then as we know that inert gas is not specified, it's not involved in the reaction, but we must also include in the degree of freedom analysis the yielding of inert gas. So from we have three unknowns, we will going to subtract with two atomic balances and one. So we have 0 degree of freedom, and therefore the system is solvable. And then we're going to do the balance the balancing of each each elements to get the molar fraction. We're going to use the atomic species balances. So in atomic species balances, we know that the input is equals to output. It's uh, it's automatic. We're using atomic species balances. So here in the uh, left hand side is the input. So uh, the input is N1, which we need to solve. But since we're going to use the atomic species balance, we must also consider the amount of each element. So in input in C2H4 in ethylene, in every 1 mole of ethylene, there are 2 moles of carbon. So 2 times N1 here. And then for the output, we're going to do the same. So we must count how many carbons are there in each element. So there are 2 moles of carbon on 1 mole of C2H4. There are also 2 moles of carbon in 1 mole of C2H5OH ethanol, and then there are four moles of carbon in 1 mole of ether. These are all in the output. So we're going to multiply the amount of um, the carbon in on each molecular fraction of um, of each compound, and then after that we're going to multiply it with the total amount of moles, which is 100. So from there, we come up with this equation. We're just going to multiply the right hand side, and after that we're going to divide it with 2 to get the N1, which is there are 46.08 moles of N1. And then for the hydrogen balance, we're going to do the same. Atomic species balance. Input is equals to output. So as I said earlier, the hydrogen is not independent because there are in uh, in N1 and N2 there are moles of hydrogen in ethylene and in water. So the here this part is the input. So the N1 that we solved earlier, um in 1 mole of C2H4 there are 4 moles of hydrogen. We're just going to count the moles of hydrogen in each compound. And then also the N2, which is water. It is in the input reactor. So in 1 mole of H2O, there are 2 moles of hydrogen. And and this part is the right hand side, the output, the product. So we're going to to just write the molar fraction of each compound as given by the um, flow given in the flow chart, uh, and then multiply it with the each uh, amount of hydrogen in each compound. So there are 4 moles of hydrogen in 1 mole of C2H4. There are 5 moles of hydrogen in 1 mole of ethanol, and there are 10 moles in 1 mole of ether. And finally, there are 2 moles of hydrogen in 1 mole of water. From after we multiply the amount of hydrogen to the molar fraction, we're going to sum it and then multiply it again to the total uh, fraction. Uh, the total moles of the product, which is 100. So after that, we're going to simplify it, and then we already solved the n1. Wait, we're going to multiply and then sum these values and then multiply it to 100. And then next, we already know the n1, so we're going to substitute the value of n1 here to 4, and then move it to the right hand side to get the value of N2, which is 47.4 moles. So from here, in next is the oxygen. I think we already solved the N2, but but I think we should also do it to verify that our calculations is correct. So the N2 is the unknown, the input, and then we're in the output. There's this total amount of moles, I mean the product. And then here's the molar fraction of each compound. We're going to count how many oxy moles of oxygen in each compound, and then multiply it to the molar fraction. And then we're going to simplify it uh, in each on the three uh, compounds that have oxygen. um, each compound has only one oxygen, so it would be easy for us to analyze it. We're going to sum this part and then multiply it to the total molar fraction. I mean the total moles of the product. And then after that, we get this value of 47.4 moles. So we can verify that our calculation for the hydrogen balance and the oxygen balance obtain the same result. And then lastly, for the inert gas balance, and it is the entry in the input. It is the unknown. And then we have this uh, the molar fraction of inert gas. We're going to multiply it to the total effluent gas, the product, which is 100. So uh, after that, we get the value of entry, which is 9.3 moles of inert gas. Then after we know the values of the input, which is 46.08 moles of C2H for ethylene, 47.4 moles of H2O water, and then 9.3 moles of inert gases. To know the molar composition of the input, we're going to sum this up, and then after we sum this up, uh, we're going to divide it with the molar fraction of the input over the uh, total moles in the input times 100. So if we do this, we can know the percentage of each the percentage molar composition of uh, each compound in the input. Okay, so which is we have 43.4 uh, in the input. We have 44.83% moles of ethylene, 46.12% of water, and then 9.05% of inert gases. These are the molar compositions of the input. And then next is the percentage conversion of C2H4, the ethylene. So mhm. We just need to know the the input of I mean the molar fraction of the input of ethylene minus the molar fraction of the output of ethylene over the um, input of the ethylene again. So yeah, 46.08 minus 43 point. This is the input here minus the output which is given minus the input which is equals to 6.03. This is the percentage conversion of ethylene. And then next is the fractional yield of ethanol. So uh, we can know the fractional yield of the ethan yeah ethanol. It is the moles of ethanol in the output. This is output over the maximum uh, molar molar fraction of uh, ethanol. It is in the input. So the maximum molar fraction of ethanol is 46.08. It is the condition we can get. It is like the condition if of like we can get its maximum value of C2H5OH if C2H4 if ethylene was fully processed and there was no side reaction occurred. So we need to know the molar fraction of C2H4 in the input which is 46.08. So we're going to divide that the 2.5 which is the output over 46.08 which is the maximum input if ever that there was no side reaction occurred. So 2.5 minus 46.08 is 0.54. And then lastly, we need to know the selectivity. Okay. So for the selectivity of C2H5OH ethanol to ether, we just need to divide the molar fractions of each compound in the output. So this is the mole of C2H mole of ethanol and this is the mole of ether. Uh, this was given in the question if we're going to look back. So the moles of ethanol is 2.5 and divided to the moles of ether which is 0.14. We divide it and then we can know the selectivity of ethanol to ether which is 70.9. Okay. So uh, I think I'm done with the first question. I'm going to discuss the second question. So for the question number two, ethylene oxide is produced by the catalytic oxidation of ethylene with the balance equation of 2C2H4 plus O2 is the product will be 2C2H4O. And then an undesired competing reaction is the combustion of ethylene. We have here the chemical balance equation of C2H4 plus 3O2 plus 2CO2 plus 2H2O. The feed to the reactor, not the fresh feed to the process, contains 3 moles of ethylene per mole of oxygen. The single pass conversion of ethylene is 20%, and for every 100 moles of ethylene consumed in the reactor, 90 moles of ethylene oxide emerges in the reactor products. A multiple unit process is used to separate the products. Ethylene and oxygen are recycled to the reactor. Ethylene oxide is sold as a product, and carbon dioxide and water are discarded. Okay. Uh, for this question, there are mentioned mm, two balance equation. One is would be the main equation, which is the yielding of ethylene oxide by the catalytic oxidation of ethylene. And then there's this side equation, the undesired competing reaction. for the combustion of ethylene. So for the first question, assume a quantity of the reactor feed stream as a basis of calculation. Draw and label the flowchart. Perform a degree of freedom analysis. Write the equations you would use to calculate the molar flow of ethylene and oxygen in the fresh feed, the production rate of ethylene oxide, and the overall conversion of uh, ethylene. Do not do calculation. Okay, so I will be assuming that there will be 100 moles that will be fed to the to the reactor. But there there again, there is a specific ratio that is said in the question uh that the feed to the reactor has ratio of 3 moles of um ethylene to, oh sorry, this must be 4. 3 moles of ethylene to 1 mole of oxygen. So uh, I think it's some sort of algae like like algebraic process to to know the ratio of the m- moles of C2H4 to 1 mole of oxygen. So with the 100 mole fed that I assigned, there will be 75 moles um, C2H4 of ethylene, and then there will be 25 moles of oxygen gas. So here is our ratio 3 is to 1. And then with respect to the 100 mole fed is 75 moles is to 25 moles here, as we can see here. And then next that we're going to do is to to do the flow chart. So we know it is mentioned what will be um, the compounds from feed to the reactor, and then what will be the compounds that will be recycled, what will be the product, and what will be discarded to the separator. Okay. As we as we're done making the flow chart, as we're done making the flow chart, what we'll be doing next is to do the degree of freedom analysis. Honestly, I'm not sure with some of my degree of freedom analysis. I don't know if I've done it correctly, but I'll try. So, since we have more than one equation, I think it's ideal to use the atomic species balance atomic species balance as we're going to as to analyze the degree of freedom of each system. So let's start at the entire process first. So this imagine this will be the whole system. We're going to examine the whole system. So there are 5 unknowns, right? So the NC2H4 from entering the mixing point, and then NO2, uh, N3, N4, and 5. These are the unknowns for the entire process, minus the 3 independent atomic gases, the carbon, hydrogen, and oxygen. So it yields to 2 degree of freedom. The next is the reactor. So for the reactor, there are 5 unknowns, N1 to N5 here, is from reactor. And then there are 3 atomic balances, the carbon, hydrogen, and oxygen. And then there are 2 additional relation. which is the percent conversion of percent the single pass conversion that is mentioned in the problem, and the ratio, the ratio of 90 moles of ethylene oxide emerges in the reactor products. So we're, we're going to subtract the unknowns to the independent atomic balances and additional reaction, and then we get the 0 degree of freedom, which means that um, the system here is solvable. We can get the unknown variables through this system, and then continue with the degree of freedom analysis in the separator. So there are five unknowns here, N1, N2, N3, N4, N5, and there are N3, N4, N5 here, and here also. Yeah, I forgot. And then there are three atomic independent atomic balances: the carbon, hydrogen, and oxygen, which is equals to 2 degree of freedom. And then for the mixing point here, we're going to do the degree of freedom analysis here. There are four unknowns: one, two, three, four here. And then there are three independent atomic balances: carbon, hydrogen, and oxygen, which is equals to 1 degree of freedom. So the ideal thing that we do here is do the solving of unknown variables here in the reactor, and after we solve this, if we are done solving this, we can next transition or the our solving of NC2H4 and NO2 here in mixing point. So we're gonna do first solve here, and after that we're going to solve the unknowns of the mixing point also. So the here what we'll be doing next is the variable calculations around the reactor. So first is the percent conversion of ethylene oxide. Uh, it is it is mentioned that the single pass conversion of ethylene is 20%. Um, Single pass conversion is defined as the reactor in the input minus no. uh react reactor of the output um w- is minus to reactor in the input. So N1, which is the output, and then on this side, on left hand side, is equals to the input. Okay, so it is said that there is 20% single pass conversion of ethylene. So we're going to subtract the percentage of ethylene in this 20% is in the output. So we should know the percentage conversion in the input, which is 1 minus 0.20 is 0.8 or 80%, times the 75% mole of ethylene. So yeah, this is our first equation. For the percentage yield, it is mentioned that there that 90 moles of ethylene oxide emerges in the reactor products. So uh, we're going to do input is equals to output. So but this side is the output, and then this side is the input. So since this part, the right hand side is the output, we're going to solve uh, with the given uh, with the given values. So this is the output. We have the 0.20, which is the single pass conversion in the output times 75 mole of C2. Oh, so this is the input rather. This is the input. 0.20% times 75 moles of C2H4 times the said um, percent yield, which is 90 moles of ethylene oxide over 100 moles. So this is our second equation. And then we're going to do the atomic species balances on each element. So we have here the carbon. So from the input, um, where atomic species balance is input is equals to output. This left hand side is our input. So 75 moles of C2H4. So as we know, there are in every 1 mole of um, C2H4, there is 2 moles of carbon. So we're going to multiply that, which it will be the input. And then the right hand side, which will be the solving for the output. So we're going to multiply the atomic speed. I mean the molar fractions of each product in the reactor to um the amount of moles of carbon in each compound in the reactor output that has carbon. So uh, in N1 is C2H. There are two carbons. In N3 is C2H4O, which has two carbons. And in N4 is C2H4, which has two carbons. We're just going to multiply and do not solve, of course. And then next is the hydrogen balance in the reactor. So this this left hand side is the input. So the multiply the molar fraction of C2H4, which is 75 times in uh the amount of so for 1 mole of C2H4 there is 4 moles of hydrogen. So we're just going to multiply that. And then on the right hand side is the same. So we, we just need to know uh the uh the amount of hydrogen of in each molar fractions of in each compound. So in 1 mole of C2H4 there is 4 moles of hydrogen. In N3 there in 1 mole of C2H4O C2H4O there is uh 4 moles of hydrogen, and in N5 in 1 mole of water there is 2 moles of hydrogen. So after that simplify it and we come up with this um, equation. And then lastly for the oxygen balance, uh, this is the input. So we need to multiply the molar fraction of O2 with the knowledge that in 1 mole of oxygen gas there is 2 moles of oxygen. And then in right hand side is the output, the unknowns. So we're just going to specify the compounds that has oxygen, and then we need to know how many moles of oxygen in each compound, and then multiply it with the um, unknown molar fraction variables. So Here's our variable. Fifth equation here, and then so as we know after we solve the variable calculations around reactor, we need to solve the variable calculation around the mixing point, so we can also solve the missing variable around there. So the for the oxygen gas balance, the it the the left hand side is then the right hand side is the output. So uh, we're going to subtract 25 minus N2, and then for the C2H4 is 75. Ah, originally the equation is N2 plus N2 is equal 25 to, and C2H4 is N2H4 plus N1 is equal to 75. This is on the left hand side is the input. But since we already N2 and the missing are not, we're going to substitute there, and then uh, to get the unknown variable, the value of NO2 and uh, so we come up with these equations. Okay, so next that we need to know is the overall conversion of C2H4. Since it is in the recycle stream for or reactor, we can assume that the overall conversion of C2H4 will be 100%. Since it is in the recycle, we are sure that all of it will be processed, all of the input C2H4, because we have this recycle stream. So the overall conversion will be 100%. Okay, so the next thing we do is solve the unknown variables. So for the equation 1, we just need to solve it to get the N1. So, and in the equation 2, we can,
Hmm?
wait again.
Okay, I think both question one and question two, you apply the atomic balance. That's right, atomic
Uh,
balance.
yeah, yeah,
Mhm.
okay, so we just need to solve the N1 and N3 for the equation 1. Then, as we know the N1 and N3, we can proceed with the solving of the next missing
Mhm.
variables. Just substitute the known variables to the equation, so that we can know the N4, and then eventually the N5, which is the molar fraction of water, and then substitute, as we know, as we solve some of the variables, we're going to substitute the uh, N1, N3, N4, and N5 to the equation 5 to get the N2, which is 30.75 moles of O2. And then, okay, so we reach this point now. So we're going to substitute known known variables to get the unknown, to get NO2, and then substitute N1 here to get the N2CH4. So 75 minus 60 is 15 moles of C2H4, or know the uh, molar flow Yeah, yeah, yeah. Okay. After we get the molar flow rates, next is to okay. Next is to calculate the molar flow rates of ethylene and oxygen in the fresh feed needed to produce 1 ton per hour of ethylene oxide. So here, I need to mm, I need to solve something so that 1 ton per hour of ethylene oxide would be yielded per hour. So I'm going to do a scale factor so that we can get the molar flow rates of ethylene and oxygen from the fresh feed that is needed to produce 1 ton of ethylene oxide. So here, 1 ton per hour. Yeah, and then multiply it so that things will be easy. We're going to convert the ton to kilogram. In every ton of C2H4, there is 1,000 kilograms of C2H4. And then to make things easier again, uh, so in every 1 kilogram of C2H4, there is 100 no, 1,000 grams of C2H4 because I want to know I want to use the unit grams. So the next is we should know the molecular weight of C2H4O. So in 1 mole of C2H4O, there is the its weight is molecular weight is 44 grams. And then finally, the 13.5 C2H4 is our, if you guys remember, it is the reactor here. The molar fraction of the C2H4O in the reactor product. And then after that, we can get this scale factor, which is 683.5 grams per mole over R per mole per hour. So after we get this scale factor, I'm going to multiply it with the moles of C2H4. I mean moles of the ethylene in the input. We have 15 here, and then the moles of O2, which is 11.25. So the target is the molar flow rate of the ethylene in and oxygen, like how many grams per mole per hour, because it's flow rate of ethylene to produce 1 ton of ethylene oxide. So I'm going to multiply it. So there is 15 times the scale factor, and then 11.25 times the scale factor. So we come up with these results. It means that to produce 1 ton per hour of ethylene oxide, we need, I mean, uh, 25,252.5 grams per mole per hour of um, ethylene and 18,939.4 grams per mole per hour of oxygen gas to produce 1 ton per hour of ethylene oxide. That's all, Ajahn. I hope you understand. You understand something from me. Yeah.
For both questions, you use the atomic balance. Would
Yes, yes.
you back
For the
to
both.
the first question? The first question.
Here.
Question one. Okay. Go to the geo definition. Aside for question one and question two, I think you apply the atomic
Atomic.
balance. And the atomic balance, you only input equal to output. For this
Yes.
case, there is no generation and no consumption term for that case. But I think the technique that you showed is straightforward. It's clear for understanding, but we would like to focus on the yield to the next page, next slide. Next.
Here.
Yes. The yield, next slide. Number 8. Okay. Where is yield? Okay, yield. Yes. The yield we have at least 3 definition yield, but for this case you use the output or the production of the ethanol divided by the maximum ethanol. The maximum ethanol means the maximum that it can be produced by the design reaction, design reaction with no side reaction. How to calculate the maximum for this? 46.08 was the maximum. The maximum, yes.
You mean this again? This value?
Yes.
Oh. I just assume.
For this case, we have 2 reactions. Two reactions. We would like to produce methanol. Aside the yield is maybe the methanol that's produced divided by the maximum methanol produced from the first reaction. 0.5. What is 0.5? And 46.08. How to calculate 46.08? How do you obtain this?
So, I think this is where I get value, but we just I think this is like theoretical.
This is
if there is no side reaction occurred. So to get the maximum.
yeah. Okay. The unit of 46.8. What the unit is more, okay? More of what? More of, okay. More of C2H6, more of ethane, that's right. More of ethane. This is the more of ethane, but for this case, more of ethanol. That's right. More of ethanol is 46.8. For this case, we calculate the maximum. That's right. This is the maximum from the first reaction. From the first reaction, the first reaction is put you back to the reaction. Okay, this is the reaction. That's right. 1 mole. Okay, these are ethene and water. That's right, ethene and water and produce ethanol. That's right. This 1 mole, 1. That's right. But for the design product, we would like to get the ethanol. But for this case, we have the side reaction. Right? Ethanol is produced ether and water also. Okay, for the yield, we have 3 definitions. The first definition that we use in the equation, we calculate from the ethanol produced divided by the maximum possible of ethanol that can be produced from the design reaction. For this design reaction is equation. This is the design reaction. That's like what is the amount of the ethanol can be produced from this reaction based on theory. Like based on theory, it means the maximum. From the theory, it's 1 mole ethane, 1 mole water produce 1 mole methanol, 1 mole ethanol. But from the balance, you get mole of ethane is 46.08, and also 111. That means the generation of ethanol also 46.08. This is the maximum. That's right. This is the maximum. This is the produced from the first reaction based on theory, but in the reality, it's not equal to this because this also convert to the another product. That's right. That means the real amount is maybe reduced based on side reaction. Okay, for this case, the real amount of ethanol produced is 2.5. That's right. 2.5. Okay, we get 2.5 divided by 46.08. Okay, and another definition you can calculate based on the amount of ethanol produced divided by the feed of limiting reactant, right? Feed or the consumption of limiting reactant. Okay, you can use 3 of this definition of the yield. It may be produced divided by the maximum production based on the desired product, or produced divided by the feed of reactant, or produced divided by the consumption of reactant. This is the definition of the yield. That's right. Okay. And the selectivity is the definition of the desired product divided by the undesired product. Right. And also the question 2, we have 2 definitions. We call the question 2, we have multiple unit operation. Would you go to the question 2, the diagram of question 2? Yeah, for this case, we diagram. Slide 10. Okay. For this case, we have at least 3 multiple units, 3 units. Okay, the conversion, we have the single part conversion and overall conversion. For single part conversion, we consider the reactor only. That's right. Reactor only, but sometimes there is no 100% conversion. If you would like to increase the conversion, you have to recycle some unreacted reactant. That's right, unreacted reactant, and sometimes you can increase the conversion based on overall conversion. The overall conversion means the amount of the reactant at the outlet. That's right. Feed minus outlet divided by the feed multiplied by 100. That's right. If there is no outlet of the feed, that means feed minus 0 divided by the feed. You get 100% conversion. That means we can use all of reactant to produce the product. This is the benefit or the helpful of the recycle. Because if we use the recycle, you can push or you can force to produce more and more product and use to more of the reactant. You can reduce the cost. If you do not have the recycle, sometimes you have to split or send out the feed or the reactant. That's right, for that case. Okay, this is the reason why we would like to incorporate recycle in our system. This is the most common used in industry. Okay, the technique that you present here is correct and your answer is correct. Have any question from audience? Okay, it's now 2 p.m. Okay, the last question. I think today is only homework and we'll stop the class. Okay, thank you for your presentation. Let's move to question 2. Question 2 from what?
Yeah, teacher.
Okay. Question 3, not question 2. Okay.
Can you see my screen?
Yes.
Okay. Question number 3. With methanol is fed to space heater at rate of 12.0 L per hour and burn with excess air. The product gas is analyzed and following dry basic percent are determined. The question number A. Draw and label a flow chart and verify the system has 0 degree of freedom. So this is my draw liquid methanol feed to space heater, and when it burns, here the question give us is 0.0045 of methanol, 0.0903 of carbon dioxide, 0.011 is CO, and I got 4 unknown is in 1, in 2, X, and in 3, minus 4 one line, or we know 4 no is C, H, O, and N. So I got 4 degrees of freedom. Next, question B. I have to calculate the fractional conversion and percent excess air and mole fraction of water. So theoretical oxygen, I got 444.9 mole oxygen per hour. C balance, I got N2 equal 2,627 mole per hour. H balance, I got 569.6 mole H2O per hour. And solving N1 equal 574.3 mole oxygen per hour and X equal 0.822 mole. Okay, I have to find the fractional conversion. So I got 0.960 mole methanol per mole feed. About the percent excess air, I got 29.1%. And the last one, mole fraction of water, I got 0.17 mole H2O per mole. Yep, that's all.
Go to back to the technique of degree of freedom analysis. Okay. How many number of degree of freedom for this?
4.
Zero. Okay.
Oh, 0.
That's right. For this case, you use the atomic balance. That's right. Atomic balance also. For the case, you use atomic balance, and also you balance of carbon, hydrogen, oxygen, and nitrogen. Okay, go to the next slide. You have to talk about the theoretical oxygen. What is it? How you obtain this? Equal to 444.9 more oxygen per hour. Could you explain in detail? 296.6 multiply 1.5. Why you have to multiply 1.5? Could you explain in detail for me about the theoretical oxygen? Why you get it 444.9?
I use this number.
Why you use that number?
It's not correct, right?
It's correct, but I ask you why you have to describe how to obtain this value. Why you multiply 1.5 with 296.6, why is equal to theoretical oxygen? What does this mean? You understand my question?
Yes.
Why the theoretical oxygen equal to 296.6 multiplied 1.1 1.1 was defined in detail like this. How you get this equal to the theoretical oxygen. Theoretical oxygen, it is the oxygen required from the complete combustion reaction. I think could you explain me why 296.6 multiplied 1.5 equal to 444.9 mole oxygen per hour? Why this term equal to this term? Why this is the amount of oxygen? Because you write only the number, I don't know what is this. Why the 296.9 multiplied 1.5 equal to amount of oxygen? I don't know. I don't understand. I don't understand. You understand that you do? Yes, I argue why you calculate this term, but equal to the mole oxygen per hour. And also why you see balance is equal to this equation and S balance equal to this equation. Oxygen balance equal to this equation. Because you show only the number, I don't know what is this. Why this number modify this number, we get this mole of oxygen. Why this to the side, we get mole of what? Something like this. This mole of carbon.
But here, in 2, and I got all of number multiplied together. That's what I got 2,627.
Okay, my first question, could you identify why the mole of theoretical oxygen you get 444.9? Could you detail of this question? think when you try to understand what you do, I think. But you show only the number. I don't know what is this. What is this? Why when you make the C balance, why you get this? You could explain why you get this question. What is it term mean? Why you get it? What is term mean?
Is from
Okay.
here.
Yes, what is it from here? Okay. Okay, the first one, why oxygen equal to this? What is it? 290.6.
Yeah, the methanol.
What is it, the methanol? The methanol use, methanol in feed, methanol in
Methanol
outlet.
free.
Why you multiply methanol feed with 1.5, you get oxygen. Why not ethanol? Why not methanol? At 96.6 mole methanol per hour, multiply 1.5. Why you get the unit is mole oxygen per hour? This is the mole methanol per hour. But this mole oxygen per hour. Why you get this?
Theoretical of oxygen.
Why you check the unit? This unit is mole methanol, mole ethanol per hour, but this unit is mole oxygen per hour. You calculate the mole of oxygen, but you multiply this by mole methanol, why you get the mole of oxygen. I think the number is correct, but I would like you explain this why. How to calculate the theoretical oxygen? Could you explain to me how to calculate the theoretical oxygen? You understand my question, right? Anyone can help Chanapat and your friend? Anyone can explain to me what? I think when you do the homework, you have to understand what you do, I think. Because you only write the number, but I don't know what you understand or not. I have to ask you, because this is the reason why I would like you present to me. I will ask you what it is, how understand or not. Anyone can explain?
Ajahn, is it correct to say that the theoretical oxygen is we want to know how much or how many moles of O2 would react based on the stoichiometric equation. So in order to get this, we need to use the mole of methanol and then multiply by the stoichiometric coefficient of O2, which is 3/2 or 1.5.
Okay, thank you. Okay. This is the theoretical oxygen that we calculate from the stoichiometry equation. That's right. Okay, could you back to the second slide, slide number 2. Yeah. For this case, we have two reactions, right? The first reaction is this is for complete reaction. This is for partial combustion. For the theoretical or maximum possible oxygen, we calculate from the complete combustion reaction. What is the complete combustion reaction and partial combustion reaction? Chanapat, what is the difference between complete combustion and partial combustion? Hello. ชนันพัฒน์ได้ยินกันไหม ฮัลโหลชนันพัฒน์ ฮัลโหลชูฮัลโหล ชนันพัฒน์ ชนันพัฒน์ได้ยินกันไหม ฮัลโหลชนันพัฒน์ ชนันพัฒน์ฮัลโหล ฮัลโหล ฮัลโหล Okay, like for the calculation, like from the theoretical, like the same previous example, we calculate boil based on the maximum possible. That's right, but we calculate based on the complete combustion reaction. The complete combustion reaction is considered the combustion to produce carbon dioxide, and partial combustion in the produce carbon monoxide. For this case, this is the complete. Equation 1 is complete, equation 2 is partial combustion. But theoretical oxygen we calculate based on the complete combustion. Right. Chanan Pat, are you hearing me? Chanan Pat, there are problems. That's why when I think when you do the homework or you do the exam, you have to explain in the exam paper what you do and what you write. For Chanan Pat presented, she also showed the number. When I read, I don't know she understand or not. She only the number. The previous question A question is okay because he write also the unit that we can cancel unit. We get someone something like this. You have to show the detail what you do. I think what is the mass balance based on component balance or species balance or molecule balance, atomic balance or extent of reaction. You have to show in the detail. That I have to show in detail. I try to check your understanding for the presentation. Is there a best technique to check your understanding? Okay, I don't know what is the Chanapat problem. Okay, the number is correct, the value is correct for Chanapat. But I don't know if she understand or not. That's right. She write by herself or not. I think I would like to check the understanding for that case. And also when you do the exam on this Sunday, when you write the material balance, it's very important. You have to specify with the unit of each value. It's very important for my understanding. That's right. When I don't understand, I would like, I have to check, ask you again, or I don't know how to give you some mark because it's difficult to understand what you understand or not for that case. I think today I also the homework presentation. This